In this video, we're going to go through some different sources of potential. So the first thing to think about is that whenever we're talking about potential, we've had some sort of separation of charges. So we have positive charges in one place, we have negative charges in the other. That means that we have an electric field, and anytime we have an electric field, whether it is uniform or not, we have a change in potential. So fundamentally, once we separate charges, we have created a potential between them. Another way to think about this is that potential fundamentally has to do with potential energy. So when I say potential here, I mean electric potential. So since electric potential has to do with potential energy, you can think that separating charges requires force over a distance, which is just work. So one of the ways that we can separate charge is actually to separate it mechanically. And how we do this is that we actually have a belt that is physically moving up and down. This is what the device looks like. You've seen something like this in lecture. And what we're going to do is make a really high voltage at the surface so that when a person touches it, her hair stands straight up. And we thought about that as there being lots of charges on the hair and the hair therefore wanting to spread out. So what actually happens here is that you have a corona discharge on a little pointy thing here. And the idea, if you remember the corona discharge, is that whenever you have a sharp point that is at potential, you have the highest electric field. So you actually have some sparking that is happening between the sharp point and the belt that puts charge onto the belt, which then is physically lifted up. And then there's another sharp thing here, which then is going to absorb the charge. Absorb is not the right word, but the charge gets transferred off. And so you then have net charge on this sphere. And you'll frequently get really, really high voltages. So we're talking about thousands of volts, and we'll talk about this as kilovolt kV, and that equals 1000 volts. So we have mechanically separated charge. You get a lot of charge at the top that makes people's hair stand up. And this does require a motor to actually run, but what's interesting about this is that you can actually crank this by hand and it will still work. It isn't that being plugged into the wall actually is doing anything other than making this spin. So that's our Van de Graaff generator, which mechanically separates charge. Another mechanical method of separating charge is a Wimshurst machine, which also generates big sparks between two electrodes. So that uses two spinning wheels that then separates the charge as well. So in this case, you don't just have one charge, but you actually keep your positive and negative charges separate. So then these two are interesting in that they're fun physics classroom demonstrations, but we don't really use them in the real world other than perhaps as background for sci-fi movies. What we use in the real world are batteries. Now, you might immediately think about wall voltage as well, but that's actually a very, very different thing. So when we think about separating charges, think about these mechanical methods, and then think about batteries, which is actually a chemical separation of charge. Now, if you've had a lot of chemistry, you might know more about the things actually going on inside batteries, but we're about to introduce a very simple model. Now, we have a little bit of terminology here. So the work done per charge is referred to as EMF, electromotive force. Don't worry too much about what that means, but it gets symbolized with this fancy scrolly E here. And if I write that by hand, it's going to look something like that. Note that it is bigger than an epsilon naught, which I frequently also write that way. So this is like capital E. So this is your E field. This is these are just two ways of writing that constant, which appears all the time, and then this means EMF. So do be careful when you're writing things that we have some similar things that are going to show up in equations that need to look a little bit different in your work, and you need to recognize when myself or the book has written different things. Now, some physics textbooks spend a lot of time talking about EMF and really stress it. We're going to see it a couple of times in the class, and what's often going to happen is you're going to immediately think of it as something different, like voltage. So we can think about the potential difference across an ideal battery, note that this is ideal, as our EMF. We're going to see EMF in some other contexts that do not just deal with batteries. So EMF is something that is basically doing work on charges, and in this case, it's going to give us a potential difference across our battery terminals. So we have this very simplified physics model of a battery. And it does use chemical reactions to separate charge, but this being a physics class, we never actually talk about those chemical reactions. So we can think about work being done to actually move the charges from a lower potential to a higher potential. This doesn't mean that we're actually lifting them against gravity, but we're lifting them to create some sort of potential energy. And so that lift here is actually what those chemical reactions are doing. So there's some sort of work done, but that's actually due to chemistry. So EMF, again, that curly E, this is how the book writes it, has to do with the work divided by charge. So if you know, work has the same units as potential energy, U, and U divided by Q is V. So this looks really similar to saying that V is equal to U divided by Q, but here we're talking about a chemical work that's being done, and so this is technically a different type of quantity. However, in ideal battery, we do actually get to set these equal to each other. So what's the limitation? Well, if current is flowing through the battery, we are frequently going to have a non-ideal battery where the voltage across it is actually smaller than the EMF. Now, this actually gets a little bit tricky, and one of the things that we'll talk about in this context are the internal resistance of batteries. We'll basically talk about it once and say that that is what makes batteries non-ideal, and we're not really going to see it again. So in general, we're going to get to say this, but do understand that this is a simplification, but it's one that we get to make almost all of the time. So the last thing we need to talk about are batteries in series. And this is a new word here, but it's going to be a term that shows up when we talk about capacitors and other components of electric circuits. So I hope that you can kind of understand what series is here, but if not, we'll talk about it in more detail when we talk about capacitors and other ways to connect things together. So the idea of series is that you're connecting things end to end. So in a really simple sense, if I want to ask what is delta V across these two terminals, well, I literally just add them up. So this would be delta V1 plus delta V2. So that's pretty simple. And this picture here shows basically an X-ray of a flashlight. And what you should know is that in a flashlight, you usually connect batteries end to end. Now remember that batteries have a pokey end and a flat end. And so if you note here, this is the flat end, this is the pokey end. This is the flat end, this is the pokey end, I think. And so if you do it that way, you notice that the pokey end always goes to the flat end. And we'll talk about a situation where that isn't true here, but for now, let's think about it that way. And hopefully when you put batteries in things, you know that they always need to go in that way. Now, interestingly, for some devices, you can flip both batteries around, like a light bulb, sorry, for like a flashlight, but for many devices, you cannot. So for many devices, you have to put them in a certain orientation. But so if each of these batteries is a 1.5 volt battery, and I don't know what type of battery it is, so it might not be, what you then get here is 3 volts. So that's one reason why you have to put lots of batteries in different types of objects, is that you actually need different voltages, not just 1.5 volts. So lastly, let's talk about this situation. So we need to start at one end, right? Let's call this x equals 0. And then we're going to think about this x final over here. And there's not really a coordinate to think about here. I just want a simple way of defining this. So as we go from the negative to the positive part of the battery, you can think about this as a delta V of plus 3 volts. But then note that this one's flipped around. We're going from positive to negative. So this is like we're going down negative 3 volts. But then we're again going from negative to positive, which is like another plus, oops, I'm sorry, this number should have been a 1. So plus 3 volts at the end. So what does that equal? Well, that equals just 3 minus 1 plus 3, which equals 5 volts. So from here to here is positive 5 volts. If you set this equal to 0, V final is then equal to 5 volts. So the orientation of batteries do actually matter, but normally we're not going to deal with this. It's just something to think about and be careful about.